Okay, then let's continue with the last bit for today, but actually with the first bit of the real course. So just to finish on the last slide. So this was now the first quick run through FMI with physical foundations, biological foundations, and some statistical foundations, of course, on a very shallow level. But so that you at least have heard that there is something like a GLM or a classifier approach to fMRI already in kind of the first 2 weeks before we now go over all of these physics, biology, and statistics to a certain degree in more detail. So the first thing then, or the second unit in the fMRI course is then essentially the physics bit and the physics data processing bit, which is called MR signal generation and static contrasts. Here I talk about the stuff as it's described in the Hüttel book, and the outline is essentially to first talk about the nuclear level, which I call nuclear spins here, then kind of the aggregate level of many nuclei called spin systems, and then to talk about the MR signal dynamics on a more global level, fairly closely connected to the spin systems, and in the end trying to give you a first idea of how one can at least do contrast, if not really images, but at least do contrast with these techniques. I have to say, and of course this is also the reason why we will revisit all of this in January, you should basically see this and also how it's presented in the Hüttel as kind of a first intro to the whole thing, which might help you to identify certain aspects that play into magnetic resonance imaging, but you should not, also not from reading the Hüttel, get the impression that you, after hearing me talk about these slides or reading the Hüttel, now really understand what's going on, because the discussion is on a level that is, because it also avoids a lot of the quantitative stuff, is on a level that is quite, in a way, superficial, where then things might not get that clear. So what I'm trying to avoid here is disappointment. On the other hand, there is no other way into this whole thing, I think, via this way, because one first needs to identify what are the key things that are then described in more detail by the quantitative theories. And then a specific thing about this whole thing is that the quantitative theories that exist for the whole thing are obviously from physics, which, if math and physics is always a little bit was a little bit problematic. And there are two descriptions. So there are, and you can in a way already see this from this outline, there are what is usually referred to as a quantum theoretic description of the whole thing, which brings up terms like spins. And there is a classical mechanics description of the whole thing, which is more related to the actually signal dynamics. What we will do in January is, and what I'm currently also more interested in, and also what I know about, is the classical mechanics dynamics viewpoint, not the quantum theoretic approach, because this quantum theoretic approach, actually, when you measure the signal and reconstruct images and so on, doesn't really play a role. However, the way these two things came about is that they're actually, when NMR, so nuclear magnetic resonance, was first studied in the first half or first to mid of the 20th century, there were different groups working on this, and some strive for a more quantum theoretic description, and other groups strive for a more classical mechanics description of the whole thing. And so you have these different levels of explanation and different forms of explanation of kind of the same thing, which then later were kind of tried to put together. It's a little bit like in statistics, where you have kind of in classical statistics the Fisher stuff on p-values, and you have the Nyman person on hypothesis testing, and then later on people try to put this together, and then you get these confusions that some people say you can never accept a null hypothesis. And I would say, well, you can if you're in the Nyman person world and so on. So it's a bit of a mess, but it's good to know that there's a bit of a mess, because then one can better identify what one actually wants to do. And what we want to do is, with this, get you a first idea of the important concepts as a preparation for then in January, so after we went through this course, to revisit the classical description of this. And it will get clearer once we did actually something, and I did not only talk about this empty slide here. So the general story, and this is the Hüttel story, starts with the idea that in biological systems there are hydrogen atoms. So think of that a big part of biological systems is actually water, and in water you have 2 hydrogen atoms and 1 oxygen atom. And the hydrogen atom, if you look at its nucleus, is of course a single proton. And these single protons, which are abundant in biological tissue, they are actually used for MRI. You can also use different nuclei for MRI, but for what we are mainly interested in, it's actually the hydrogen nuclei. So for the moment we fix the hydrogen nuclei, and we have to talk about what kind of properties they have. So the thing is, the crucial thing to get started on this is that the hydrogen nuclei have both electromagnetic properties, so it's a charge, and they have also classical mechanics properties, so they have a mass. And the fundamental idea is that they have a magnetic moment, which is often abbreviated μ. And once you start reading about this, you will find that sometimes the magnetic moment is understood as a quantity, so as a quantitative scalar thing. So a magnetic moment of, let's say, 32. And sometimes it's understood as a vector, so as a quantity that has both a magnitude and a direction in 3D. And one has to actually, when one reads these physics books, pay quite some attention about what they are talking at a given moment. They could make it easier by explicitly saying that. But anyway, there is something called a magnetic moment that is generated by the spinning charge. And if one formally looks into what the magnetic moment actually is, then it's defined as a torque, which doesn't really help because you're also not really familiar with what a torque is. But then you know what a force is, at least. I think you've all seen Newton's law with F equals m times a. So it's a torque is something like a force, but it's a turning force. And it's basically what this magnetic moment describes is the force that is exerted on such a thing when it's put into a magnetic field. Yeah, so the idea is always in physics that you do these kind of experiments where you put something somewhere and then something happens. And here you would have something that is like a proton, and you put it into a magnetic field, and then sometimes something happens. If you start thinking really, so in physics they talk about energy and force and so all the time. these things don't exist, right? So these are models of the world, and I think in physics they don't really know what energy is. They just have it as a thing that it's very useful for modeling phenomena. So don't try to figure out too much what a force is or what an energy is. It's all about that you put two things together and something happens and you try to describe that, and then you say, okay, that's the force that does that. So when things fall down, that's the gravitational force. That's physics. Now, the thing here in this context, to get started with this, is that they have a magnetic moment, these protons, so in a way one can also think about them as little magnets. And this is actually already getting to the classical model. So what you see here next to each other is actually a kind of a visualization of both the quantum and the atomic level description and the classical mechanics level description, because for most of the formulas that then actually apply, one can think of these protons as little magnets that might actually move. The thing is, with the little magnets and all the protons, one can appreciate that they also have a mass, and this is actually spinning. So it's not that important to really get into why there's a magnetic moment and why there's an angular momentum. What matters in the end is the differential equation for the magnetic moment. And I'm writing currently on the stuff that we do in January, and I will avoid talking about these things. We will start in January, we'll start with the basic differential equation for the evolution of a magnetic moment is mu cross product the magnetic field, and done. And this is a modeling assumption, because all of this sounds like this follows from nature and it's really clear, but it's a modeling assumption. Yeah? But it's an intro to the whole thing. Now, why is this interesting? For two reasons. First thing is that if these little hydrogen protons have magnetic properties, then it's fairly easy conceivable that if there's another magnetic field, namely the magnetic field generated by the scanner, which is very strong, that this strong magnetic field has some kind of effect on these little magnets. Yeah? So think in kind of intuitively or picturesque way that in the water that is in a biological system, there are all these little magnets which are hydrogen nuclei, and now they are put into a very strong magnetic field. So basically doing something that you never should do. So basically take a little magnet into the scanner and see what happens. And what you will see, and what you are kind of also familiar from like playing with magnets in school or at home or whatever, is that they will move, and it also is fairly intuitive that that they will align with the magnetic field, because I will give you an analogy from gravitation in a second, because in a way this is most energy efficient and most stable. I will show you an example for that from gravitation in a second. Yeah. So the first thing to appreciate is that there are these little magnetic things in biological tissues, specifically in the water molecules. You put them into a very strong external magnetic field in the MR scanner, and they spatially align with the external field. Now, here you see already that they align in two ways, some of them parallel and some of them anti-parallel. Another consequence of this alignment versus non-alignment is that if you think about these are little magnets, right? And you look at the magnetic field that they actually produce. Then the idea is, if they are not aligned, then all these random orientations of the magnets cancel out, and the sum of all magnetic moments is small. Now, if they are aligned, and if there is a little bit of a difference between the number of ones that are aligned parallel and anti-parallel, they actually create a small magnetic field that you can measure. Yeah. So again, the intuitive idea is randomly oriented magnets. You put them into a magnetic field. They align, and because now a majority of them is actually aligned in the parallel state, you can, if you have a very sensitive measurement device, of course, because there's this very strong magnetic field, if you look for the difference in terms of let's say the excess of magnetic power or magnetism in this system, you will find a little bit, yeah, because these little magnets now also produce something in addition to the strong external magnetic field. Wow, actually also this morning I wondered why I have this at this point. I mean, what this kind of shows is the intuition that, yeah, maybe for this reason, if you have a very strong magnetic field and you have small magnets, they will essentially align with the magnetic field lines of the strong magnet. It's all on this kind of intuitive, picturesque, first-hand experience level, this explanation. Now, what is maybe going away from this first-hand experience level, but is very important, and actually is also the first thing that we will discuss when we look at this quantitatively, is that such a system that spins around its axis and has mass behaves essentially like a gyroscope. Yeah? So, and this is now really shows actually three different models of this thing next to each other. So this is kind of showing a spin, kind of a hydrogen proton. This shows the little magnet model of the spin next to it. And this shows, so this is a magnet in a magnetic field, and this shows the classical mechanics thing in a gravitational field model of these two things. Yeah. So in physics, the same equations that govern a gyroscope that precesses are used to describe a magnet that, so a gyroscope that precesses in a gravitational field. The same equations are used to describe the precession of a magnet in a magnetic field. And again, these same equations are thought to govern the spin as it, because that's a magnet precessing in a magnetic field. Yeah? In terms of the terms that we need for it's raining. The terms that we need for magnetic resonance imaging, these things are important because this precession that happens, and I will show you what precession really means in a second, happens at a specific frequency. And this frequency is determined by the field strength. So the stronger the field, so the stronger the magnetic field, the higher the frequency of precession, and it depends on the nucleus. We are only talking about hydrogen nuclei here, so this constant is always fixed. But yeah, the important thing is that there is a frequency of precession. This frequency of precession is called Lama frequency. It depends on the strength of the magnetic field, which also means, and this you might keep in the back of your head, that if you change the magnetic field, for example, by a gradient coil over space, that you have different precession frequencies over space, right? So if you change the B over space, and you look at the same nucleus with the same gyromagnetic constant, then the precession frequency will change. Now, to link this back also to the angular momentum, the angle at which this precession happens depends on the angular momentum. Now, what is precession? This is precession. See this? Yeah. So precession is a term that you might have not heard before. it's called gyroscopic motion, so it's based on this classical mechanics thing that you might have played with as a kid. So a gyroscope, ein Kreisel, yeah, that you turn, and then under the assumption that there is no energy loss by friction, what happens is that if this thing spins, and it spins around its own axis, as you can see here, if this spins in a gravitational field, it remains so you see the top of the gyroscope here, it remains in this kind of dynamic position that the top of the gyroscope spins around the axis of the gravitational field. Of course, you assume that here there's the bottom, here's the top, and this is generated by this interaction between the gravitational field and the spinning of the mass of the gyroscope itself. Yeah? So one can quantitatively describe it, but that doesn't really change the intuition. So this movement of the top and of the whole thing around the gravitational field axis created by the gravitational field and the movement of the thing about its own axis, that's precession. Questions about precession? What is precession? Right now.
I have a question on the dependency. So is the angle and velocity is like two different things, or are they dependent on each other, like two determined each other?
Yeah, I mean, there are multiple things, right? So there is at one point, so there is once there's the frequency of the thing around the general axis, there is the frequency of the thing around its own axis, and there's the angle. And the angle and the frequency, they can be assumed independent. So
but the spin around itself, but the angular frequency is, of course, somehow dependent on the angle.
Yeah.
Like this one.
Yeah. The thing is, this is an interesting question. Of course, one can only really address that if one writes down the model and looks at what's actually going on and makes the right assumption. So there are different kinds of, if you look into the physics literature, there are different kind of precession models that all work a little bit different. And we will look at one where these things are essentially independent. So, but that's for January. But it's a good question. I mean, it's not necessarily trivial. It depends on how one sets up this model. So the important thing from this, what you should get, is that these hydrogen nuclei or nuclear magnetic moments or spins, are referring to the same thing, precess, meaning they precess around the axis, so they do this kind of wobbling movement around the axis of the magnetic field. And this being due to the fact that there is this magnetic field and that they themselves have magnetic properties and mass. Now, at the same time, what's happening is that they either align parallel or anti-parallel to the main magnetic field. So they either do their precession kind of in the upward direction in respect to the magnetic field lines, or in the downward direction. And here the idea is that this is called the parallel state. It's the low energy state, and it's more stable and hence slightly more abundant, while this anti-parallel state is a high energy state, hence unstable and slightly less abundant. So that there is a net surplus or a net magnetic field generated by these parallel state magnets, little magnets, nuclear magnets. So how can one appreciate that? And of course, this is again exactly the model that is behind that. So what's happening there in physics is that you first had these classical phenomena that you can observe, and that were horribly boring in school when you played like with gravity and so on. I think it got more interesting in school when you did things like electro stuff or maybe relativity or something, but these mechanic things, they were really boring. But what happens in physics is that these descriptions, and also mainly the quantitative descriptions that were successful, let's say at this macroscopic mechanical level, they were then also imposed on other phenomena. And coming from the macroscopic world, I think it's really, or it's fairly intuitive to appreciate that if you have kind of a lever here, and this is kind of, allows to rotate. So if you put up kind of a handle or whatever like this, that if you give it a little tip, it of course will turn around and end up like this. So it's and you need to put in energy to get it into that. So if you tip it here, it will assume this position quite easily. But if it's in this position and you want to put it in this, you have to actually. Can I also sign this? Or? No, I don't think it's for me.
Whoever's administrating the WhatsApp group.
I don't want to.
I think you're the administrator, no? Okay. We all are.
So I think it's easier appreciated that you need to put in energy to get from this yellow thing into this. And that this is unstable in gravitation, and this is stable. So if you tip this a little bit, it will maybe move a little bit, but it will stay essentially in this position. Where here, if you just give it a little tip, it will assume the more stable position. Yeah.
What do you mean in this context by slightly more or less abundant?
More or less. So there are more.
Like in terms of.
Number, in terms of number. Yeah. So there are more. So the idea is that if we go back to the slide before, that there are 3 in the parallel state and there are only 2 in the anti-parallel state. Yeah? It's just because they are more stable. The idea is that by chance, but not really by chance, because there's this energy driving them into this direction, there are more. The reason why this needs to be assumed is because there is something that you can measure. Yeah? So you have to think about, again, how these little models come about. Things turns out that if you put a biological thing into a strong magnetic field, you can actually measure an additional magnetic field, and then you have to think about where's this coming from, and then you can come up with this kind of explanation. Yeah? So there must be a little bit more of that. Okay, so that's now kind of a description at the nuclear level, so at the hydrogen proton level. But you also have to think about, of course, that this explanation was not the first thing, or that this explanation actually was discovered in any way. So it's not that the first thing physicists did when they had this MR machine here, they had kind of this ingenious way to look at how protons behave, and looked really closely, and then I say, okay, so these protons behave like this. So then if we look more macroscopically, then this must follow. Of course, it was the other way around. So they have kind of a, like I just said, they have kind of a macroscopic way to measure something, and this explanation on the nuclear level is, of course, a post hoc explanation, like whole quantum theory. And quantum theory only came about in the early half of the 20th century, and not and classical physics like Newtonian physics and so on had been around much longer, right? So it's what's happening at the microscopic level. This is, of course, a post hoc explanation of what you observe on a macroscopic level. But if you present this, is of course nice if you start from the small thing, and then it all makes sense that it's these kind of things happening on larger levels. course, it's usually not the case, and it doesn't really make sense, but in any case. So this is what we've just seen, and this is also what we've just seen because I'm going backwards actually. Sorry, this is now the level that we want to talk about. So what the MR technique really measures is not what each individual proton is doing. It's also, if you think about fMRI, it's not what each individual neuron is doing, but this is of course a completely different level in terms of size. So the MR technique doesn't measure the single behavior of the single proton, but it measures the net magnetization M of all nuclei in a volume. And the idea is to describe this vector M, and you see this vector M here, first of all dynamically, and then as an entity in 3D space. So what you should think about this M is that it's a list of 3 numbers. I don't think I have that on this slide, but we will see that again. So you all know, I hope, what a vector in physics is, so, and maybe also what a vector in math is. So if you want to describe a vector like this with respect to some origin, let's say at 0, you need 3 numbers, the x, the y, and the z coordinate. You can put them one below each other, then you have a 3D vector. And if you visualize this vector with respect to some origin, you have this little arrow, and then you can make the components larger or smaller. We will see that also on these slides a little bit more formal, and we will definitely see that in general very formal, because this vector, this net magnetization vector, this is what is really modeled and described in terms of magnetic resonance imaging. Now this vector has of course 3 components, and they come with specific labels, and this is also something one should get used to. So the z direction, so if you think about a 3D Cartesian coordinate system with x, y, and z, the z direction is called longitudinal, which goes in line with the fact that the z direction in MR imaging is always along the magnetic field lines. And if you think again of how the magnetic field of the scanner looked like, maybe I'll show you that again because then it's easier. Oops. So the scanner field looks like this. It's called. Oh, so sorry. The scanner field looks like this. Go away. This is the field generated by the Helmholtz coils, and in the scanner bore, so inside the scanner where the participants are put, the field lines go from the feet of the participant to the head, so that's the direction, and this is the z direction, yeah? And this is fixed. So of course one could do it differently, but this is convention in MR imaging and also fMRI and so on. It's always this, that is the z direction, and this is also called the longitudinal direction. So these are essentially terms that you need to become familiar with, so that when somebody says longitudinal component, you know that this is kind of the z direction. In addition to this longitudinal component, there is the xy component that is perpendicular to the external field, so that is in the xy plane, and that's called the transverse component. Now the fundamental thing is that if nothing happens, so if you have these many nuclei inside the specimen that you put into the scanner, and they align parallel and antiparallel, the net magnetization, because they all precess at different in different phases, the net magnetization is purely along the Z direction. This means that if you put in the specimen into the strong magnetic field and you measure the additional magnetic field that is now due to the probe or the specimen or the brain or whatever that you put in, this has only an amplitude in the Z direction, in the resting state, so if nothing else happens. Yeah? And this is it's kind of intuitive in the sense that they align their precession with the magnetic field. There are more in the parallel state than in the antiparallel state, so it's in the same direction, and they precess in all different phases. So some are currently, as you see here, some are currently here in the circle, some are here in the circle. So this all cancels out. What remains is that there is some amplitude, some power in the Z direction. Yeah. So this is something essentially you can also just memorize in the at equilibrium. There is just a magnetic moment in the Z direction, and then you don't have to worry about why that is. Just memorize it. Then you know that, and it helps you to get into actually the quantitative description. Now, this net magnetization, as I said, one can measure it, but one cannot really do much with it. So if you just measure this net magnetization, you cannot really do imaging with it. You cannot do contrast or anything with it. So what you have to do is, like often when you measure something, you have to perturb it. And this one can basically describe by this analogy of a scale. So if you want to, so here, I don't know, this bottle or something, if you want to measure its weight, if it's just standing there, you will not be able to measure its weight. You maybe estimate it, but you cannot really measure it on a scale. So if you want to measure it, you have to put it on a scale. So you have to perturb it. So maybe you put it up to onto this scale that is shown here. You might also have the scale at the very same thing, and then it just exerts its pressure on the scale here. But then again, of course, you put it on the table first. So the thing is, if it's just at equilibrium, if a system is just at equilibrium, you cannot really measure it, so you need to perturb it. And this you are familiar with by putting, if you measure a weight, you have to lift it and then let it exert its mass power, essentially, and get to equilibrium again. Yeah. So why this perturbation? Because that's the next thing that happens in magnetic resonance imaging. Now that the system has this, the spin system has this magnetic moment, a radio frequency pulse is delivered. You can also say a weak oscillating magnetic field, which is called B1, is turned on, but it's usually referred to as a radio frequency pulse. And this now perturbs the system from equilibrium. And this is really hard to understand. I think even on this, the way it's described here, specifically in the quantum framework, this is really not, I don't think it's actually understandable at all. But there is a way to understand that actually in the classical sense, if one models what happens if one does the same thing in terms of aligning. So one way to think about it is that you have these little magnets. They align with a magnetic field, and they precess. And now you actually, in this kind of precession frame of reference, you turn on another magnetic field. And then because you're appreciating that the first magnetic field did something, the other magnetic field also can do something. This is what we really want to go in more detail in January, because this needs the rotating reference frame and so on. And it's a little bit more demanding. here you can, if you want, you can live with this, which is the quantum description of the whole thing, that some of the low energy state precessing nuclei are turned into the high energy state. So definitely something changes for the magnetization vector and getting it away from equilibrium. And you also can appreciate at this point that you need this radio frequency pulse. So there's this radio frequency pulse, which is called also excitation. And this perturbs the equilibrium magnetization vector. Yeah? How one can think about this a little bit clearer than like, okay, there is somehow the sine wave and somehow then this happens, is actually, if you read the Hüttel book, it's this rotating reference frame thing, but it's a box there. It's not very well explained. It's actually also not explained very well in most physics books. So this really needs a little bit more devotion and time than I want to spend on this right now. Good. One can, and maybe this is then the last thing, depending on how strong and how long one turns on this radio frequency or oscillating magnetic field, one can perturb the net magnetization vector and tilt it more or less. And this is what you also will read in fMRI papers. They always say flip angle 90 degree or 80 degree or something. This refers to how much this net magnetization vector is actually tilted by means of the radio frequency pulse, and one classically distinguishes a 90 degree excitation pulse, which tilts the net magnetization into the transverse plane, meaning the XY plane, or 180 degree excitation pulse, which completely inverts the magnetization vector. Yeah, so that's the flip angle. And now, maybe, do we see a picture of this? No. Now the crucial thing is why this is also important. We will see a picture of that later on. The MR signal that is measured is actually measured only in the XY plane. This is something you also should, from this, we will see it again, but you should appreciate that if the net magnetization is how it is in the beginning, so if it's oriented like this in parallel to the magnetic field, the machine is actually blind to it. It doesn't see it. It only measures what happens in the XY direction, and thus it measures nothing. If it's tilted into the XY plane, then it can measure something. And we will come back and talk about this many times, but this is also why such a 90 degree excitation pulse, so tilting the net magnetization by 90 degrees, is interesting, because then you get a magnetization that you can actually measure. You can of course also do a 100 degree excitation pulse, and then what will happen, and this is then the next big topic, is that this thing will move back to equilibrium, and then at one point it also sweeps essentially through the XY plane, and you can measure that. But so these are kind of two terms at this point to appreciate that you can tilt this net magnetization vector, and you can tilt it by applying energy, radio frequencies, electromagnetic power, and you can either apply a lot of energy, then you can tilt the whole thing, or you apply a little bit of energy and then you only tilt it by 90 degrees. So, and maybe I stop on this. So the thing is that once you put in energy and tilted this net magnetization vector, or at the quantum level, you change some some anti-parallel to the parallel state. Some parallel to the anti-parallel state. these will want to return to equilibrium. The net magnetization vector wants to get back to equilibrium, or the ones that are now anti-parallel and are in the high energy state want to go back. And they then, without further putting something into that, return to equilibrium. And it's actually this process of returning to equilibrium and the energy or the magnetic field that is emitted in this process that is measured. So this induces, so this electromagnetic energy, this magnetic field of returning to equilibrium, this induces a current in the detector coil of the scanner and is measured to then make fancy pictures of the brain or all other sorts of things. So yeah, I think that's a good point to stop.
I have a question. Yeah. How can the scanner distinguish between molecules? So what makes oxygenated blood special? Because all atoms consist of hydrogen.
Yeah, okay, so there are a couple of things that you are mixing there. So first of all, what the whole thing depends on the signal that you then also measure depends on the precession frequency. So let's go back to that. Oops, edit. So the first thing is that a given nucleus has a specific gyromagnetic ratio, and for a constant magnetic field, the precession happens at a given frequency and is also measured at this frequency. Yeah. So you basically, in terms of, this is going ahead, so we haven't really discussed the details yet. But this is where this is coming from. So you have the hydrogen nuclei; they have a specific Lambda frequency, and if you then get the signal, you also get a frequency at this Lambda frequency. You know that this is from hydrogen nuclei, essentially. Okay. So you can, if you tune the whole thing, and also if you do the radio frequency pulse at a different frequency, you can also tune the scanner to not work with hydrogen nuclei, but work with some other kind of nucleus, for example, phosphor or whatever. So that's the one thing. The other thing that you intermix there is that the deoxygenated and oxygenated hemoglobin, they do something completely different. So what they do is they change the magnetic field in a location. Yeah. So they lead to a signal dropout because they disturb the magnetic field in the imaging of the hydrogen nuclei. Yeah. So it's not that it's so the hydrogen nuclei, they are measured, and then the deoxyglobin comes in and messes up the signal essentially. But it's not that it's the hydrogen or the water in the hydrogen, I guess, in a deoxyhemoglobin molecule. I mean, they are so amino acids. There must be, I guess, there are hydrogen nuclei also in amino acids. Haven't looked into that for a long time, but yeah. So, but that's kind of the idea. So that you have kind of these little magnets in there, which are the hydrogen protons, and you also in this kind of setting you assume that they are spatially constant over space, which of course not the case because they diffuse and you have water diffusion and so on. That's why you can do diffusion imaging. But yeah, they are there, give the signal, and then comes the dioxide. Yeah, but we will yeah go about this more often. Other questions? Okay, then I guess I see you next week.